Imagine standing beneath a velvet sky, scattered with countless stars. For thousands of years, people everywhere have looked up, searching for meaning in those distant lights. Stars have inspired our stories, guided our journeys, and marked the passage of time. They are woven into our myths and mysteries, connecting us to the universe beyond. With each new tool, from simple eyes to powerful telescopes, we have uncovered more of the cosmos's secrets. Our own Milky Way is just one of billions of galaxies, each a city of stars. The atoms in our bodies, our world, and everything we know were forged in the hearts of ancient stars. When we gaze at the night sky, we are looking at our cosmic ancestors. Join us as we journey into the heart of the stars to discover not only their story, but our own. Why do stars shine? How are they born? What happens when they die? These are some of the most fundamental questions we can ask about the universe. Over the last few centuries, a revolution has occurred. Through science and observation, we have begun to pull back the celestial curtain. We have discovered that stars are physical objects governed by the same laws of nature that operate here on Earth. They are colossal spheres of superheated gas, primarily hydrogen and helium, powered by nuclear fusion. Without stars, the universe would be a cold, dark, and empty place. Every element heavier than hydrogen and helium was created inside the fiery hearts of stars. When massive stars reach the end of their lives, they explode in brilliant events called supernova. So, when we look up at the stars, we are looking at the engines of cosmic creation. In this guide, we will journey through the entire life cycle of a star. At its heart, a star is a gigantic, glowing ball of hot gas, mostly hydrogen and helium. Every particle is pulled inwards by gravity, creating immense pressure and heat in the core. Temperatures of millions of degrees Celsius trigger nuclear fusion. Hydrogen atoms fuse to form helium, releasing colossal energy as light and heat. This energy counteracts gravity, creating a balance that can last for billions of years. The light journeys from the core to the surface, then travels across the universe. When you see a star, you are witnessing ancient light, energy forged in a cosmic furnace. Every star is a testament to this cosmic balancing act, illuminating the universe. Not all stars are created equal. Just as people come in different shapes and sizes, stars exhibit a breathtaking diversity. Astronomers classify stars based on their temperature, which also determines their color. The hottest stars are blue, burning fuel fast and living short lives. Cooler stars shine red and live incredibly long. Our sun is a yellow-white star with a moderate temperature and lifespan. This range creates a stunning stellar rainbow. The spectral type classification uses letters like O, B, A, F, G, K, and M. Star sizes are incredibly varied. Red dwarfs can be Jupiter-sized, while supergiants are enormous. This variety makes the universe rich and dynamic. Each star plays a different role in the cosmic ecosystem. Where do we find these brilliant cosmic objects? Stars aren't spread uniformly across the universe. Like people, they gather in groups. The largest gatherings are galaxies, immense gravitationally bound systems of stars, stellar remnants, interstellar gas, dust, and dark matter. Our sun is one of hundreds of billions of stars in the Milky Way galaxy. When you look at the faint milky band of light across the night sky, you're looking into the dense, star-filled plane of our galactic home. Every star you see is a close neighbor. Within galaxies, stars form smaller groups called star clusters. Open clusters are loose collections of young stars born from the same gas cloud. The Pleiades, or Seven Sisters, is a famous open cluster. These clusters are cosmic nurseries, snapshots of stellar siblings in their youth. Globular clusters are vast, spherical collections of very old stars, packed tightly together. They orbit in the halo of galaxies, like ancient satellites, offering clues about the early universe. Beyond clusters, most stars exist in small groups or as solitary wanderers. More than half of all stars are in binary or multiple star systems, locked in a gravitational dance. These systems can lead to complex interactions, influencing each other's evolution. From lone travelers to vast galactic cities, stars populate the universe in a cosmic web. Every star begins its life in darkness and cold, not fire, within vast nebulae. These breathtaking cosmic clouds are stellar nurseries where new suns are born. Stretching hundreds of light years, they contain enough matter to form millions of stars. Composed of hydrogen, helium, and dust, these clouds drift for millions of years, their gravity too weak to collapse. A trigger, like a supernova or a passing galaxy, sends shock waves that compress the gas and dust, creating denser pockets. Gravity gains the upper hand, and the cloud fragments into smaller, denser clumps, each a seed for a new star. These clumps, called Bok globules, are dark cocoons where collapse accelerates. Gravity pulls material inward, the cloud spins, and a star's life begins. Once a clump of gas and dust collapses under its own gravity, there is no turning back. Over time, gravity pulls more material inward, converting energy into heat, warming the core. The once frigid cloud begins to glow with infrared light, becoming a protostar. Still embedded within its cocoon, it's invisible in ordinary light. Infrared telescopes pierce the dust, revealing incredible activity as the protostar grows, accreting material. The surrounding material flattens into an accretion disk, funneling material. From this disk, planets, moons, asteroids, and comets will form. Powerful jets blast out from the poles, creating bipolar outflows. These jets create glowing Herbig-Haro objects, signaling the birth of a new star. The protostar phase is a crucial stage in a star's life. For millions of years, the protostar grows, its core becoming denser and hotter. Gravity squeezes the material at its center, and the temperature rises to millions of degrees. When the core temperature hits 10 million degrees Celsius, nuclear fusion begins. This is the moment of ignition, the moment a protostar is truly born and becomes a star. A new source of light and heat bursts into existence. The onset of nuclear fusion creates a tremendous outward push of energy. A new balance is established, a state of hydrostatic equilibrium. This balance marks the beginning of its long, stable life. The new star unleashes a powerful stellar wind, blowing away the remaining cocoon of gas and dust. The star emerges from its nursery, shining brightly. Once a star ignites, it enters the main sequence, the longest, most stable phase of its life. Our Sun is a main sequence star in this phase for 4.6 billion years and will remain so for about 10 billion. During this time, gravity pulling inward is balanced by the outward pressure from hydrogen fusion in the core. Most stars, over 90%, are main sequence stars. A star's mass determines how long it stays on the main sequence. Massive stars burn fuel fast and live short, brilliant lives. Red dwarfs burn slowly and can last for trillions of years. The main sequence is a long, stable period where stars do their most important work. Nothing lasts forever, not even the stars. Eventually, a main sequence star will run out of hydrogen in its core. When this happens, the star's stable life ends. Gravity gains the upper hand and the core contracts. The layers of hydrogen ignite and the star's outer layers expand enormously, growing to hundreds of times its original size. The star becomes a red giant. This is the fate that awaits our Sun. The fate of a star from this point on depends on its mass. For the most massive stars, they become red supergiants, some of the largest objects in the universe. These supergiants fuse progressively heavier elements. Iron is a dead end for fusion. The star's engine has finally run out of road. For the most massive stars, the formation of an iron core marks the beginning of a spectacular end. Gravity overwhelms the star, causing its core to collapse in less than a second, shrinking to an object of unimaginable density. The outer layers crash down, rebounding off the core and unleashing a titanic shockwave. Supercharged by a burst of neutrinos, this shockwave tears the star apart in a Type II supernova. For a brief moment, the explosion outshines an entire galaxy, radiating with the brilliance of 100 billion suns. But this is also a moment of creation. The supernova forges elements heavier than iron, gold, platinum, uranium, scattering them across space. These elements seed new stars, planets, and life itself. The iron in your blood and the calcium in your bones were born in such cosmic violence. Lower mass stars, like our Sun, end more gently, shedding their outer layers to form glowing planetary nebulae, a final, graceful farewell. The star's core remains behind, a quiet ember in the vastness of space. What remains after a star dies depends on its mass. Low-mass stars leave behind white dwarfs, Earth-sized, sun-mass embers that cool for billions of years. A teaspoon of white dwarf material would weigh tons, but these remnants eventually fade into darkness. More massive stars create neutron stars, city-sized objects with the mass of the Sun, so dense a sugar cube would outweigh all of humanity. Some neutron stars spin rapidly, emitting beams of radiation as pulsars. The most massive stars collapse further, forming black holes, regions where gravity is so strong, not even light escapes. White dwarfs, neutron stars, and black holes make up the cosmic graveyard, the final states of stellar evolution. These remnants are the universe's most extreme objects, shaped by gravity's relentless pull. Each tells the story of a star's life and death, influencing galaxies for eons. Even in death, stars shape the cosmos, their legacy echoing through space and time. The universe is home to stellar extremes that defy imagination. Stephenson 2.18, a red hypergiant, is the largest known star so vast it would engulf Saturn's orbit if placed at our Sun's center. R13601, the most massive star, packs over 260 solar masses and shines nearly 9 million times brighter than our Sun. The hottest known star, WR102, blazes at 210,000 degrees Celsius, stripping away its own layers in a furious wind. At the other end, EBLM J055557 AB is barely bigger than Jupiter, just massive enough to ignite fusion. These record breakers showcase the diversity of stars, from giants that dwarf our solar system to tiny embers on the edge of stardom. Some stars live fast and die young in spectacular explosions. Others burn slowly for eons. The stellar family is as varied as it is vast, each member pushing the limits of physics. From the largest to the smallest, stars reveal the universe's boundless creativity. Their extremes remind us how much more there is to discover. Not all stars fit the mold, some are just plain strange. Tabby's star, for example, dims unpredictably, baffling astronomers and sparking wild theories from comet swarms to alien megastructures. In binary systems, stellar vampires like white dwarfs steal gas from companions, igniting novas or detonating as supernovae. Magnetars, a rare type of neutron star, wield magnetic fields so powerful they could tear atoms apart from thousands of kilometers away. These monsters unleash bursts of X-rays and gamma rays, briefly outshining entire galaxies. Some stars, like IPTF-14 refuse to die, exploding as supernovae multiple times, defying our understanding of stellar death. Theories suggest these zombie stars shed layers in repeated eruptions before their final collapse. The universe is full of stellar oddities, each challenging what we think we know. Even after centuries of study, the stars continue to surprise us. Their mysteries keep us looking up, searching for answers. The story of stars stretches far into the future. In 5 billion years, our sun will swell into a red giant, likely engulfing Earth before shedding its outer layers as a planetary nebula. Its core will become a white dwarf, fading slowly over trillions of years. Red dwarfs, the smallest and most efficient stars, will outlast all others, shining for trillions of years as the universe grows dimmer. Eventually, even these ancient stars will exhaust their fuel, leaving only white dwarfs, neutron stars, and black holes. Star formation will cease, and the cosmos will enter the degenerate era, a realm of darkness and silence. Occasionally, stellar remnants may collide, sparking brief flashes of light in the cosmic night. But the age of bright stars will be over, replaced by the slow fade of their remnants. The universe's future belongs to these exotic corpses, silent witnesses to a once brilliant cosmos. Even as the lights go out, the legacy of the stars endures, written across the fabric of space and time. As the degenerate era unfolds, even stellar remnants will decay. White dwarfs will cool into black dwarfs, cold, inert spheres invisible in the darkness. Over trillions of years, gravitational interactions will dissolve galaxies. Their contents scatter into the expanding void, leaving a diffuse collection of black dwarfs, neutron stars, and rogue planets. The universe becomes increasingly empty as the black hole era begins. Eventually, even black dwarfs and neutron stars may vanish through proton decay, evaporating into low-energy particles. The only objects remaining will be black holes, slowly swallowing stray matter. But even black holes evaporate over immense timescales via Hawking radiation, leaking energy and gradually losing mass. A supermassive black hole could take a Google years to completely evaporate. One by one, the last black holes will radiate away, leaving a faint whisper of particles. This leads to the heat death. The cosmos will be a vast, cold, uniform sea of fundamental particles adrift in darkness. All structure and memory of the star-filled universe will be gone. This is the ultimate fate of the cosmos, a slow fading into an endless, quiet night. From nebula dust to black holes, the story of stars is the story of the universe. They come in all shapes and sizes, from tiny red dwarfs to colossal hypergiants. These celestial engines forge the elements that make up our world and our bodies. When we gaze up at the night sky, we look back in time, witnessing the cosmic cycle that makes our existence possible. The stars remind us of the universe's scale and our place within it. Studying them reveals the laws of physics and our cosmic origins. With new discoveries, we reveal a universe stranger and more complex than imagined. They challenge us to keep asking the biggest questions. So, look up. Remember each star's story and the journey of its light. We live in a brief, shining moment. By understanding them, we understand ourselves and our home. The story of the stars is our story.